where now these are vectors or transpose of vectors, and this is a matrix. So we'll write down first some symmetry relations for or some properties, symmetry properties rather, of this matrix D. So D, remember, is related to the second derivative of the total energy of the system with respect to this motion of the atoms from their equilibrium positions. So the first, so what we are writing now, are the symmetry properties of D. This will be used later. So first is this is sort of obvious in the sense that d mu nu r minus r primed is related to the second derivative of total energy with respect to u mu at r, u nu at r primed. So if you just interchange the order of these derivatives, then you get this. So obviously they are equal. The second point is
so we actually cannot see probably because of glare.
Can you see or no? Is it clear? Just 1 second. Is it better?
Yes, sir.
Okay, so the second point is that if we interchange R and R prime, so basically this means that D of R is equal to D of minus R. So how do we get that? So again, this follows from the firstly that D's are related to the second derivatives of the total energy, and third, secondly, so if I have a crystal, notice two things. One, any lattice. So if you consider the lattice points, any lattice is centrosymmetric, meaning it has a center of symmetry. In fact, you can take any lattice point to be the center of symmetry. So if you sort of invert the lattice, you get the same lattice. This is not true of a crystal. If you have basis, then you have to be careful. But if you are in, if you have a monatomic lattice, every lattice is centrosymmetric. If you reflect it or invert it with respect to any point, you get back the same lattice. So therefore, okay. So with that, I can write d mu nu which is related to the second derivative now. Given this point, which is, let's say, at R, so if this point is R, and this is some U at R, and say this is R primed, and this is some U R primed. If I invert both U and R, so if I take R to R minus R and make U to minus U, okay, so basically if instead of giving this distortion, if I give this distortion instead, I'll get the same value for D, right? Because of this centrosymmetric nature of this lattice. So then in this expression, for each component of mu, if I write minus u and I change the sign of the corresponding lattice vectors, I'll get the same D. With a minus sign. All right. Now these two minus signs will of course cancel each other. So what you are left with is the second derivative of u with respect to u mu at minus r and u nu at minus r prime, which is nothing but interchanging the signs of these two in this. So basically that by definition is u r primed minus r. So which is what I wrote here. So that's the second symmetry property. And the first and the second taken together would give you okay, so this is the second one. And what was the first one? The first one was so now you can equate these two, which gives you d mu nu r minus r primed is d mu mu r minus. In other words, D is a symmetric matrix. And finally, the third point, the third symmetry property. So what we are trying to get at is this quantity. So for this, you consider a situation where all u's are equal. And let's say you, at any r, is a vector which is, how do I write that? Whose components are right here. Is d mu for any r. So then I can write now in the situation where all the displacements are the same, so all u mu's are same, all u mu's are same. And then therefore one of these summations r or r prime will just give me n times the summation due to the other one. And for u mu, I will write the constant d mu. And this. And because d mu and d mu are constants, so I'll pull this out. And there I have sum over r. Sorry, once I have written this, I can do this. Now, what is the meaning of giving the same displacement to all the atoms? I'm just rigidly translating the crystal, which does not cost me any energy because space is homogeneous. So therefore, this whole thing to start with is 0. So this is 0. So therefore, this is 0. Now here in d mu, everything is constant. So then this quantity must be 0. So that shows that this is 0. All right, so these are the properties that we will use later on. And as before, we now consider that there is a 3-dimensional crystal with one atom per primitive cell, in which the atoms are moving. So if I want to write the equation of motion of a particular atom, How do I write that? So m is the mass of an atom. So u in the harmonic approximation. And from the expression for u harmonic that we wrote, we can write this as sum for r primed. So that is for the with component. So therefore, in a general vector notation, I can write this as well, D is now the matrix. Primed. And as before, because we are studying vibrations of atoms in the crystal, we seek solutions that are in plane wave form. So we seek solutions that are of this forms. So the thing to notice here is that this is now a three-dimensional vector. So is this one. So in a one-dimensional crystal, there was nothing. This was not important because the atoms vibrate only in one direction. But now, because we are in a 3D crystal, so this is a three-dimensional vector, and so that will, in general, be different for different directions. So you plug this into this equation, and what you get is second derivative of time will give you omega square. So eventually what you get is will be r primed here. So you can do some transformation here, which will give you this was r primed. Vector. Now this quantity which is like the Fourier transform of D of R, is denoted as D of K. So what have we got here? We have got like an eigenvalue equation for K for D of K. So this matrix D, this is called the dynamical matrix. And this omega squareds are the eigenvalues, apart from this factor of n. Sometimes this D over n is called the dynamical matrix, and omega squares are the eigenvalues that give you the energies of the vibrational modes. So for n, again, for n values of K in the Brillouin zone, we will get 3n eigenvalues, because this is a 3 by 3 matrix and it has 3 eigenvalues. So for n values of K, we'll get 3n eigenvalues. And these epsilons will give you the corresponding eigenvectors. So these are the normal modes of vibration of this three-dimensional crystal. There are n atoms in 3 dimensions, so you have 3n normal modes. And the omega squared, once you calculate omega squared, the corresponding omegas are the frequencies. So omega k's are the frequencies of the normal modes. And these 3 vectors at each k. So these are called, if I remember correctly, these are called polarization vectors. So these give you the sort of directions of vibrations of the normal mode. So yeah, so that's about the nomenclature. Now let us see what we get, what is the behavior of these modes as at small k's as before. So we need to look at this matrix, because eigenvalues of decay are the ones that give us these energies. So so the first thing what I'll do is, see, R goes over all the vectors. So if we have some particular R in the summation, we also have minus R in the summation. So we'll split this into those 2 parts and divide it by a factor of 2. So in one part I will write R. In the other part I'll write minus R. But we just saw that d of minus R is same as d of R. So this will become d of R. Okay. But then sum over R, T of R, was 0. That was the third symmetry property we derived. So I can easily add a constant here without changing the value of this. Okay, so these two will give me twice of cos theta, that is cos k dot r, and I can pull the 2's outside, which will cancel this factor of half. So I get and which is so what do we have here? So we have a matrix D of K, which is a real matrix, which is an even function of K because of this, and so a real symmetric matrix. Okay, so it will have real eigenvalues. So when I wrote that eigenvalue equation, D of K epsilon was m omega squared epsilon k, I'll get real eigenvalues. So just to, and there will be 3 of them. Okay, so I can write each one of them as epsilon I. So in other words, the corresponding omega I would be, so how do I write that? Okay, so this, let me write as some epsilon lambda I epsilon I. So then this omega I k, I is 1, 2, and 3. Omega k is equal to lambda I over m. This will depend on k. So these are the frequencies of my normal mode. And because we are solving eigenvalues for a real symmetric matrix, the eigenvectors would be orthogonal to each other. So now dk is this, which depends on k squared for small k. Okay, this sine squared k dot r.
Sir, can you add some ink to the pen? I mean, the letters have become very.
Unfortunately, I don't have another pen and I don't have ink. So, I mean, I was not at all prepared for this. So, this is the best I could do, short of canceling the class once again. Because I normally don't use this. Okay, so small k. At some angles it is writing well, at some other angles it is not. So we are looking at small k's. Dk is -2 squared. Half of unit vector k times r squared. So the eigenvalue equation then becomes, for at any k, for small k's, the eigenvalue equation becomes please check the factors and all that. In case I made some mistake. Okay. Now this is just a unit vector. Okay. So the value of k is here, k squared. So omega is k squared. So therefore, omega I k for any sort of I is something that depends on, actually it should depend on the direction of k only and k. So omega is proportional to k. So we again get, so the point here is that we again get a linear dispersion in this 3D monatomic crystal, which we should, because as we argued earlier, this is a consequence of the fact that we have broken the continuous translational symmetry of free space in constructing the crystal. So therefore, we should have excitations that go to 0, and in particular here it goes as k. It's not necessary that it has to go as k, but these modes go as k at small k. So, and the c comes from the eigenvalue of this equation. So this is the point. So again, we have these acoustic branches. Now we'll have 3 acoustic branches. Whether the 3 branches will have exactly the same dispersion or not, it depends on the crystal symmetry. They need not. So what happens when you have a 3-dimensional crystal with more than 1 atoms in the basis? I'll not go into the details, but essentially you will have exactly what you had in the case of 1D crystal. Namely, you will have 3 acoustic branches because you have to have 3 branches whose energies go to 0 as k goes to 0. And then you will have a bunch of optical branches. So if there are n atoms in the primitive cell, you will have 3 acoustic branches and 3n minus 3 optical branches. All right, so what time is it? Do you have any questions at this point? Let me also comment that these are the normal modes of vibration of all the atoms in the crystal that you have. So this whole analysis is, assuming that they are at some equilibrium of energy. As you move the atoms, there's a restoring force, and within the harmonic approximation, we have done all this analysis. Now, as you have done in small vibrations, if the position of the atoms from where you started this analysis happens to be not local equilibrium, then that will show up in imaginary frequencies of these normal modes. So when you do such a calculation, and in fact, we can routinely do such calculations for real crystals, not within this sort of simplistic approximation. Here, for example, we haven't discussed how to calculate the quantity d of r and the d of k, whose eigenvalues are the vibrational frequencies, but one can do much more realistic calculations. And if it so happens that the structure you have taken is not a stable one, then that will show up in the form of imaginary frequencies of these vibrational modes. So these are called dynamical instability of the system. So it would rather try to go to some other structure. Okay. Any questions?